Okay, this is going to be our fifth. Okay, well that's not a good start. This is going to be our fifth video in our series on sources of magnetic field. In this video, we're going to be covering everything from section 28.5 in the text, and what we're going to be looking at here is the magnetic field of a circular current loop. Okay, so let's kind of try and get the picture on screen here. So in this section, we're going to be looking at the magnetic field produced by this circular loop that we can kind of see here. It has a radius of A, okay? It's carrying current I. We can kind of see the direction of the current here going around it kind of counterclockwise. And to get the magnetic field of this thing, we can apply the Biot-Savart law. And we're going to try and find the magnetic field at a point P, which sits somewhere on the axis of this loop. So this is a key fact here. We have to make sure that we're always on the axis of this loop, some distance x out. If we want to try and apply this to some point that's not on the axis, this is going to break down and none of this is going to work. It's actually much more complicated to calculate these things at different points that are not on the axis. Okay. We're going to see that like we often do, because we're on the axis here, we have some nice symmetries that we can take advantage of and do some cancellations that make our job a lot easier here. Okay. So let's get down to it. We'll do the calculation. There's a little more to this section after the calculation, but we'll get to that in a bit here. I want to try and keep this thing on screen as we do this, so we'll see how this works out. Okay, so to get the magnetic field at this point P, we're going to need to add up all the tiny contributions. We can imagine breaking this ring up into a bunch of tiny sections and adding up all those contributions as we go around the ring, as we sort of integrate around the ring, right? Now there is a way to treat this thing in a sort of fully polar coordinates sense and actually do the integral in polar coordinates. We're not going to do that here. I'm going to do it exactly the way the textbook does it, and maybe I will do the full-blown sort of polar coordinates treatment of this problem in our weekly meeting. I'm not sure yet. I might choose a different problem, but we'll see. Okay, so the way the textbook does this is they're essentially saying that, well, we want to calculate B at that point P. This is going to be equal to the sum or the integral of all of these tiny little dBs that are going to be the contributions from all these tiny little segments of length around the circle here. And our dB, our vector dB, comes from the Biot-Savart law, right? So we know we can write down the Biot-Savart law like this, and we're going to have I dl crossed, and we're just going to write it in vector form here, r, so we're going to have an r cubed in the basement, okay? Except that let's take a close look at what's going on here. We can simplify things a lot already, because we can see that our dl segment, and it's kind of weird to think about it like this because we're just looking at dl at one point here, and dl is gonna kind of rotate around this ring as we go. But at this one point here, we can see that dl, which points in the z hat direction, is perpendicular to our r here. Now we have to be kind of careful, right? Well, there's a whole plane of things that are perpendicular to dl, right? You could imagine any vector that points in any of these directions as you rotate around would be perpendicular to dl. But r is one of those vectors, and since it's perpendicular, we can kind of make a big simplification here. This cross product is kind of going to go away. Okay. Also, what we should note is that our dB, our actual contribution to the magnetic field at the point P, is perpendicular to r also, and it's also perpendicular to dl. So it's a little bit hard to see from this diagram, but you can imagine that dl and r, which are mutually perpendicular, right? This is supposed to be a right angle here, but you can't quite see it because of the way the diagram is drawn, and I'm not sure how to draw it with the correct perspective here, but basically something like that. The angle formed by dl and r is 90 degrees in the plane defined by dl and r, right? You can imagine drawing a plane that contains dl and r. It would look something like this, right? But then normal to the plane, something pointing directly out of the plane, would be perpendicular to both dl and r, and that is the direction in which our dB points. Okay, so just think about it for a little bit here. You can see it, that dB is perpendicular to r, and it's also perpendicular to dl. Okay, so because of this, we're going to be able to get rid of this cross product. But before I start writing that down, let's just take a look at our dB and kind of see that we could break it up. At least this one contribution that we're seeing here, we could break up into its y and its x components, right? We could split this dB into its y component and into its x component, right? Now, we can imagine what's going to happen as this dl starts rotating around, right? So here the dl sits in such a way that it points only in the positive z direction, right? It points only in the k hat direction. But as it starts rotating around, it's going to point a little bit in the negative y hat or in the negative j hat direction, and then it's going to end up pointing just in the negative j hat direction, and then it'll start pointing a bit in the k hat and negative j hat direction as it rotates around. There's going to be a sort of complicated thing to keep track of. But luckily, because of the symmetry of the problem, we're not going to have to. Why is that? It's because we can see what's going to kind of happen to these dBys, right? So as we go around, every point along the circle is going to contribute another one of these dBys, right? It's going to keep going around and around like this, all the way around. And if we think about the way that this is going to work out, all of these dBys are going to be the same length. You can imagine this is like making like a little circle here. These are all going to add up in such a way that they're going to cancel out. So all of the contributions to our dB in the, well, what we're calling y direction now, but it's not really the y direction because it's going to end up being a little bit in the y and a little bit in the z direction, and then fully in the z direction when it's over here or over here, and then back to being in the y direction when it's over here. But they're all going to add up in such a way that they're all going to cancel out, right? They're all going to be exactly balanced, pointing outward to this sort of circle that I drew here before in such a way that they all cancel out. And so we're only going to have a contribution in the x direction here. Each one of these is going to still have a little bit of an x contribution, and they're slowly just going to pile up. Each one just adds up, and so we get only contribution in the x direction here, okay? And so this is one of the major simplifications. First simplification is that this cross product goes away because of all of these mutually perpendicular vectors. Second part is we don't even have to worry about what's happening sort of radially here. We don't have to worry about our dBy and our dBz that we can slowly break out of this thing and everything. All of those are going to cancel out, and all we have to worry about is what's going on in the axial direction here. We only have to worry about what's going on along this x direction, okay? So let's go back to writing down some stuff here so that we can actually continue the calculation. So from all this, we're going to see that our dB is really going to point only in the x direction, and so it's going to end up being dB I hat. Okay, so we're only picking up, we're picking up other contributions as we go around, but we know that when we add them all together, they're all going to cancel out. So the only one we have to worry about tracking is the dBx kind of in the I hat direction. So we could even think of this as dBx in the I hat direction. Okay, and we can write our dB. We can write our dB, just the magnitude of it, as a magnitude, because we just talked about how this cross product thing is going to end up canceling out because everything is mutually perpendicular, right? So we can end up writing our dB as mu naught over 4 pi. Basically just looking at this expression that we have up here, we're going to end up with an I dl, and there's no more cross product because these are perpendicular, and we don't even need information about the direction. We just argued that the direction is all going to be pointing in the x direction here. And so we're going to have an r upstairs, and an r cubed in the basement from here. Well, this r and one of these r's are going to cancel, and we're just going to end up with a mu naught. I'm going to write the I over here, 4 pi, and we'll have a dl over r squared. Okay? Okay, so we have the magnitude of our dB, okay? But we need to know what r is, right? We want r in terms of x and a, ideally, so that we can more easily maybe do this integral. Although we still don't know how we're going to write down dl, right? Because we have to integrate over dl, and we just said that dl is kind of a bit of a mess, right? dl is going to be some combination of stuff pointing in the k hat direction and in the y hat direction. Both of those will sometimes be positive and negative, and they're going to change the amounts of j hat and k hat as we go around the circle. So we'll worry about that in a second. But for now, let's break this up. This is the full dB, but we only want the part that points in the x direction, in the I hat direction, right? We just argued how we don't really care about the part that's pointing in the y hat direction here, or I should say j hat direction here. We only care about the part that points in the x direction. So let's write this out. Our dbx is going to be equal to, well, it's going to be equal to the dB that we have here times the cosine of theta. Let's think about why that is, okay? Because no matter where we end up, right, we're going to be going around this thing, around and around, and just like our dby contributions are going to trace out a circle. And now it's kind of tough to draw this because we're kind of trying to draw a 3D situation in 2D here, but you can imagine that our dBs are going to be tracing out kind of a smaller circle, right? Like they're going to be tracing out a circle that kind of points, well, it would kind of be closer to us in the perspective of the drawing that we have here, right? So it would be kind of pointing up in that direction. But no matter where we are on that circle, it's always going to be true that if we take the length of this dB and we multiply it by the cosine of theta, right, we're going to get this adjacent length here, because we're dealing with cosine, right? So cosine is always going to be adjacent over hypotenuse, and so we're going to get the length of this dbx all the way around each time we do that, right? So the cosine of theta times dB really does give us dbx for every contribution all the way around the circle, okay? And again, let me get rid of this to not make a huge mess. Okay. So since that's the case, we can just copy down what we have here for dB and add in this cos x, but we don't really want to write it like cos x. We're going to want to write it in terms of a and x, okay? Or I shouldn't say cos x, I should say cos theta. So we're going to end up with this expression from just above, right? We have 4 pi, then we have dl over x squared plus a squared, right? Because we have our r squared. Oh, did I talk about the length of r? I did not. Okay, so I'm going to talk about the length. Actually, let me before I make that simplification, let me write it down one more time like this. Then we're going to have cos theta here. But we want to write r in terms of a and x, and we want to write cos theta in terms of a and x. Well, r in terms of a and x are pretty simple, right? Because we're just going to end up with an a squared plus x squared square rooted, right? Pythagoras. This is the hypotenuse of this triangle here. And so r equals square root a squared plus x squared, which means that r squared is simply a squared plus x squared. Okay, so we can substitute that in for our r squared. What about cos theta? Well, cos theta is just our adjacent angle over our hypotenuse. Well, the adjacent angle to theta here, or the adjacent side to our angle theta, is a, right? And it's just going to go over the r that we just talked about. So our cos theta is simply going to end up being a over our r here, which is square root a squared plus x squared. Okay, and so we can rewrite this. I'm not sure if it's cleaner, but at least in a form that we can work with more easily. So mu naught I over 4 pi, then we have dl over a squared plus x squared, and then we have a over square root x squared plus a squared. Okay, this can be cleaned up a little bit more, so I'll clean it up a little more here, and I'm running out of space, but we should be okay. So our dbx, okay, is going to end up being mu naught I 4 pi, and this is now just cleaning up this stuff here. We're going to end up with an x squared plus a squared to the 3 over 2 in the basement, x squared plus a squared to the 3 over 2 in the basement, and upstairs we still have a dl and an a. Okay, so that is our dbx. Okay, and this is what needs to be integrated over dl to be able to get our full bx contribution. Now we could do the same thing for dby, right? We could write down dby equals db, but now it would be sine theta, right? If we look at this over here, why is it sine theta? Well, for the same reason, right? If this angle in here is theta, as we rotate around the whole thing, it's always theta. Well, then this length here, this opposite side length, which is really our dby, and will change, you know, from dby to some combination of dby and dbz or whatever as we go around, it's always going to have this length of db sine theta. So we could write it like this, and then we could simplify this thing out as we did for dbx, but we just talked about how we don't care about that contribution, right? That contribution is going to cancel, because as we go around, we're going to pick up the exact opposite on the opposite sides no matter where we are, and so the whole thing is just going to cancel out. So we can just ignore the actual form that dby is going to take. We're not going to bother integrating over it because we know the whole thing is going to clean up. Okay, so we're not going to bother writing that down, and we'll just keep working with dbx. Okay, so we want, let's keep our eye on the prize here. Let's remember we want b at P, right, our point P over here. Okay, we know it's only going to have an I hat component, right? And so again, let me rewrite that B is going to be equal to bx I hat, which is going to be equal to the integral of dbx, pointing in the I hat direction, right? And so our bx is obviously going to be equal to the integral of dbx, right? And now we're in a position where we can sort of write out what this integral is going to be. We have the integrand up here, and so we're gonna be integrating over the loop. I'm just going to write it like this. We need to integrate over the whole loop. Okay, so when I say that, what do I mean? I mean we need to integrate over this whole loop. We need to go around the whole loop. So we're integrating over the whole loop, and it's the integral of this expression that we have up here. So the expression that we have here is just mu naught I 4 pi, and I'm not going to factor anything out yet because we need to sort of talk about what we want to factor out. dl a x squared plus a squared all to the 3 over 2. Okay? So now it's important that we actually get a handle on what dl is. dl is really what we want to be integrating over, but dl is this kind of messy thing. We don't really know how to integrate over that. What are we going to do? I mean, we could go into polar coordinates here. We could have left our cosine theta in terms of theta and then integrate it over the whole circle. But the book chooses to do it by really using the symmetries to make the integrals as simple as possible, and I think that's fine. And as I mentioned, we might take a look at the other version of this later. But for now, what is dl, right? Well, if we tried to write out dl, we can see that dl is kind of going to go around the circle. So dl would end up being some combination of stuff pointing in the j hat direction plus stuff pointing in the k hat direction, and this stuff would be there'd have to be some dy in there, and there'd have to be some dz in there, and then you would have to worry about where on the circle you were. So you'd have to worry about some angle in here that I'm going to call phi. You'd have to imagine this phi kind of like going around the circle as we go around, right? So maybe I shouldn't include all that there, but let's say we call that phi. This thing would kind of depend somehow on phi, and this thing would depend on phi also, and it would be kind of a messy thing, and we'd have to worry about doing all that integration. But we can see that even though this thing would depend on y or dy and would depend on dz, you'd have to integrate over dy and dz. As you're doing that integral, there's nothing in here that depends on z or y. Only the dl might have some z or y dependence. All this other stuff is constant. Our a is constant. It's just the radius of the circle. It's never changing. Our x is constant. X is never changing. It's just the distance along the axis of our loop all the way out to the point P, right? So none of this stuff changes, so we can rewrite this whole thing, pulling all that stuff out, and so we end up with mu I over 4 pi. Then we have an a over x squared plus a squared to the 3 over 2, and we just have this integral over the loop of dl, right? So we still have the problem, but at least we've isolated our dl. I mean, in theory, we would still need to do this terrible integral that involves dy's and dz's. It would be some double integral or something, or at least we'd have to break it up into two integrals and add it up, and it would be pretty nasty. But what does this really mean? What does it mean to do an integral over this loop, right, over this loop of dl? Well, what that means is that we're going around the loop, adding up all these tiny dl's, all these tiny little segments of length, tiny little segment of length, another one, all the way around. We're adding all these up until we make it all the way back around the circle. We have to go around the circle from 0 to 2 pi all the way around, right? So if we were to do that, what would we end up getting? Well, we're just going to end up getting the circumference of the circle back. If we integrate over this circular loop, this line integral, building up all these little elements of dl to the full length around the loop, well, this is just the circumference of the loop, right? And we know that the circumference of our loop is just going to be, well, it's going to be 2 pi r, but our r here is really a, so it's just going to end up giving us 2 pi a, okay? So with the sort of simplifications we've made, this integral becomes sort of trivial. We just pick up a 2 pi a, and we can, maybe I'll rewrite it here. We're going to see, how much space do I have? Okay, I have space. So we're going to see that our bx is going to end up being mu naught I over 4 pi a over x squared plus a squared to the 3 over 2, but now times 2 pi a, right? These a's are going to end up giving us an a squared. These pi's are going to cancel. This 2 will cancel a 2 from here, and so we end up getting bx is equal to mu naught I over, what's the best way to collect this up? We can collect this up like this, let's say. Mu naught I will say a squared, 2 x squared plus a squared to the 3 over 2. Okay? That is our bx. And we know that our bx is going to point in the x direction. It's going to point in the I hat direction here, right? Because all the other contributions have canceled out. So the only magnetic field present along the axis here is only the part in the x direction. Okay? And that's exactly what the textbook gives us. They basically do it very similarly to the way that I did it here, and like I said, we might look at a different way later. So this is the expression, just to sort of sum up this example, this is the expression for the magnetic field on the axis, so it has to be on the axis of a circular current carrying loop. This is its magnitude. We know it points in the I hat direction. This is our magnetic constant, our current, the radius of our loop, and the distance along the axis from the center of the loop. Okay. So what about the direction, the sort of pointing of these magnetic fields? If we're just given a loop, we can calculate. We kind of saw how we can calculate the magnitude. We argued about how we could figure out the direction, but there's also a right-hand rule that applies here too. If you have a current carrying loop, and you place your hand in the center of the loop and you curl your fingers in the direction that the current is going around the loop, your thumb will always point in the direction of the magnetic field. Okay, so your thumb is always going to point in the direction of the magnetic field on that axis of the loop, right? If you're off that central line that runs through the center of the loop, well, then your magnetic field is going to be more complicated. And we're going to take a look at a picture of that in a little bit, but not just yet. Okay, so that is the magnetic field of a current carrying loop. But what now do we get if we consider a bunch of these loops? Let's say n loops stacked tightly in a coil, right? So we have all these loops stacked tightly in a coil. We're going to say that they all have the same radius. Okay, so it's not like a situation where they're sort of concentric circles getting larger and larger, but they're all of the same radius. So they're kind of stacked on top of each other, but they're packed very, very closely on top of each other, right? We can imagine. Can I draw it here? Maybe I draw it down here. So we can imagine sort of a loop like this with an axis for our loop like this. But then we have another loop just packed very, very tightly, like right on top of it. Okay, and we can have a whole bunch of these. These can be very, very thin and stacked on top of each other. They're stacked tightly enough that the distance, okay, that the distance from the field point in X, like let's say we're interested in some, maybe I drew this too small here, but let's say we're interested in some point P out here, that this distance is going to be the same for basically all of them, right? So within reasonable rounding error, let's say, these are all going to be about the same distance from our point P, right? So R is going to be the same for all the loops approximately, right? If that's a good approximation, then we can simply just take n times our previous result, right? We had the result over here. Just take n times that result. So I just threw an n in here because we just have n loops all stacked up. So each of those loops contributes one time the magnetic field contribution. So we have n loops. So we have n times that magnetic field contribution, right? And now, let's say we're interested in the magnetic field at the center of that loop. So we're interested in the magnetic field at the very center of that loop, where x goes to 0, right? So this is normally x. Let's say we shrink this down and we're looking at the point right in the center of the loop. Well, if we let x go to 0 here, we can see that in the basement we simply end up with an a squared to the 3 over 2, so that's just a to the 3. So the a to the 3 on the bottom kills off the 2 on top. We just end up with a single a in the basement, and this is the expression that we end up with. Okay, and so this is the magnetic field at the center of n circular current carrying loops, right? So we have a coil with n loops. And again, magnetic field or magnetic constant, the number of our loops, like how many loops we have, the current, and the radius of our loop here. Okay, so if we now take, let's say we take equation 1 over here. Okay, where do I have equation 1? No, further down. Right. So let's say we take equation 1 here, where we've written down this expression for the magnetic field along the axis of n loops of current carrying wire. What does the magnetic field look like, or at least what does the magnetic field's magnitude look like as we move over x, right? So we can imagine that we're letting x vary here, so we're letting our point P move upward and downward and backward and forward. So it's moving like, well, okay, it's only moving in one dimension, so I probably shouldn't have said backward and forward, but it's basically moving along this line wherever it wants to. If we plot that out, if we let x vary along this axis here, and in this direction we're looking at magnetic field strength, we see that we get the strongest magnetic field where x is equal to 0. So we get the strongest magnetic field, maybe I'll do this in a different color, like blue. We get the strongest magnetic field here, right? That point corresponds to this point here, right, which gives us the strongest magnetic field. And then as we move out, let's say we move up some distance, let's say this is A. So if we move some distance A in this direction, or some distance A in this direction, we end up at these points, right? And so we have some less strong magnetic field at that point, right? These are somewhat less than our B max, right? And if we move out to 2A, right? I guess I'll only do one more of these, but if we move out to 2A in this direction or 2A in this direction, we're going to end up with some much less intense magnetic field out here, right? So we can see that the magnetic field is strongest at the very center of the loop, and as we move out along the axis, and we have to stay on that axis because our expression is only valid along this axis, we can see that the magnetic field strength dies off quite quickly, okay? And so so there's kind of a sort of punchline to this whole discussion about the magnetic field outside of our coil here, and we're going to kind of get to it. In chapter 27, we discussed that a magnetic dipole moment, so that the magnetic dipole moment of a current carrying a loop with n coils is given by the expression that we see here, right? So we saw this in chapter 27. Mu is equal to NIA, where A is the area of our loop, right? And in the case of a circular loop, which is what we're dealing with here, our capital A is just pi a squared, where a little a is the radius of the loop, right? So this expression simply goes to this as we replace capital A for pi small a squared, right? If we then take this expression here and we substitute this back into equation 1 from here, we can see that we have NIA squared, so we just have to worry about getting a pi in there. We're going to end up with an extra pi in the basement. But we end up with this expression here, okay? And so this is an expression for the strength of the magnetic field along the axis of our coil, written in terms of its magnetic dipole moment, right? This mu here is the magnetic dipole moment. This mu naught is our magnetic constant, right? So we have mu naught times mu over all this stuff, and this is the extra pi that we picked up because of getting this factor in there, right? So this is an expression for the magnetic field strength for any number of loops, and that information about the number of loops is carried in our magnetic dipole moment because the number of loops will affect the value of our magnetic dipole moment, right? And so like I said, we're getting to the punchline here, and the punchline of this is that just like current carrying wires or moving charge, magnetic dipoles both respond to magnetic fields, like if you put a magnetic dipole in a magnetic field, it's going to feel a force from that magnetic field, but it also produces its own magnetic field, right? So just like, again, a current carrying wire or a moving charge, it produces magnetic field, and it is affected by magnetic field if you place it in a magnetic field, okay? So that's kind of a key takeaway from this. Anything that's producing magnetic field for us that we've looked at so far also is affected by a magnetic field, and vice versa, okay? The last thing I wanted to look at here is just this sort of drawing of what the magnetic field in a sort of cross-section kind of looks like around our current carrying loop. So you can imagine this is just 1/4 of our current carrying loop here, and this is the sort of axis along which we were looking at our point P. This is what we called X before, and you can see the shape that the magnetic field lines take here. You can see again they're sort of guided by the right-hand rule. If you were to grab this current carrying wire with your right hand, your fingers would curl in the direction of our magnetic field lines. Your thumb would be in the direction of the current, and you can see that in the very center of this, along where these two planes hit, this is our axis, right? This is our axis this way, and this is where our magnetic field is the strongest, right? According to our plot that we saw here. Okay. So that is what the magnetic field looks like around our current carrying loop, and we could imagine stacking a bunch of these loops tightly together and getting a much stronger magnetic field, right? I guess the last sort of takeaway from this is note that these are not circular, right? The magnetic field lines are not circular like they would be around a straight wire. The magnetic field kind of squishes itself as you get to the inside of the loop, right? These things are kind of crushed into like elliptical shapes because we're kind of squeezing the magnetic field and getting a much stronger field. We're kind of squeezing them all together and ending up with a much stronger field right along the axis that runs through the center of our loop. Okay. There was an example in the text for this section. It's example 28.6. I've decided not to do it to save a little bit of time here. It's really a very simple example. They just take the expression that we developed here and sub in some numbers. So there's not really a lot to learn with that one. You guys can go back and do it yourselves for sure if you'd like to see how this works. But it's basically just taking expression 1 or yeah, I'm not sure if they use expression 1 or expression 2 here, and they just sub in a bunch of numbers and solve for b, and then do it again. So instead of doing it, I decided to just leave it up to you guys, and that'll save us a couple of minutes. So I'll leave the video here for now, and I'll see you guys in the next one.